Good evening, everyone. On behalf of the House of Sultan Chand and Sons Private Limited and Method I once again take this opportunity to welcome you all to this AI webinar. It feels great to have you all here, and we thank you for that. A bit about the House of Sultan Chand first. Pioneers in the field of book publishing in post-independent India, we cater to students from primary to university level, churning out over 600 regular titles, besides adding new ones to our stable year after year. Known for competently written, elegantly produced, and reasonably priced books, our publications are widely prescribed in reputed schools and colleges across the country as well as in some other nations also. Thanks to your patronage, SCS today is a name to be reckoned with in the field of education. Our authors are distinguished academicians, professors, and educationists with vast experience and expertise. We are proud to be associated with them. I now introduce you to the host of today's webinar, Dr. Sachin Gupta, author of the hugely popular Artificial Intelligence textbooks for classes 9 to 12. Dr. Gupta is Dean, Research and Innovation, Maharaja Agrasen Institute of Technology, Guru Gobind Singh Indraprastha University, Delhi. Besides, Dr. Gupta has also been HOD, Computer Science Engineering and MCA Department, Dronacharya Group of Institutions, Deputy Director and Head, Computer Science Department, Chandraprabhu Jain College of Higher Studies, affiliated to GGSIT. With a teaching experience of over 23 years, which includes teaching undergraduate and postgraduate students and researchers, Dr. Gupta's academic pursuits have been fairly meritorious, winning him several awards, distinctions, scholarships, including the Certificate of Academic Excellence by GGSIP. It's a matter of great pride for us that Dr. Gupta's book, Decoding Artificial Intelligence, has won the Outstanding Contribution to AI Literature Award. Dr. Gupta has also contributed to various journals, conferences, and books for schools and higher education, both nationally and internationally. His achievements are truly commendable. I now invite the man himself to take you through today's session. Thank you, Dr. Sachin Gupta.
Thank you so much, sir. Happy Janmashtami to everyone who is joining us today. And I see a lot of friends who have previously been with us uh, for most of the sessions. So today one is very interesting. Interesting because there is a backstory. I'll just try to relate. We started out with big data as a specialization in the BTech program I was running back in 2016. And then it was more like just emerging. So with big data emerging back then, the challenge was somebody asked me, how do you define big data? Can anybody try to take a guess? How would I define big data? If you have to answer this question today, maybe in the chat, maybe if you can, if you want to open your mic and speak, works both for me. And no definition is wrong. Anything. Akib says large amount of data. How large, Akib? Take a guess, anything. I mean, you know the units of volumes of data, anything which works for Gurbinder, Monica, Subhashini, anything, any guesses? Okay, Gurbinder says very, very big data. Big, so it's already big. Correct. Jigna. All right. I'll start with something very basic, fundamental. For anything which we want to process on our computer, there are two things that we require. One is we should have a good computation power. That is a given must. So whatever your CPU is, we go around with a lot of different like Intel series. We had Pentium, then we have i3, i5, i7, i11. they keep on increasing that what is the actual compute of them, or how much number of operations they can do per nanosecond. That is the kind of system it works. The second big requirement is that we must have some RAM. That amount of RAM would decide that how much data can I load in the working memory of my system. So if I have 16 gigabytes of RAM, I can only run as many applications which would fit in within this 16 gigabytes. In addition to, there is an operating system that we have, which is already running. So for my Mac, for instance, there is roughly 8 gigabytes of space that my operating system and its associated functions take. So that leaves me with only 8 gigabyte of RAM, which is usable as of now. If I am opening multiple applications, operating system multitask, so it can open multiple different applications in your RAM, but at the same time, you will not be using all of them. The amount which they would take in the operational RAM, or the amount a browser would take, plus your music player is going to take there, and this meeting is also taking some amount of RAM. All of that together gives me how much memory is being used by my OS, plus the application. Any data which fits within this bound of your RAM is not big for you. But if I try to add an application which requires 32 gigabytes of storage on RAM, that would become big data for me. So the technical definition back then was that anything which would not fit in the RAM of my machine is big data for me. And that is even true for today. But we went beyond technical definition because of new technology that evolved around, that was cloud computing. So with cloud computing, this limitation of having something fit within the RAM of my system actually disappeared. Now we could purchase some space on the cloud, computation space. We could purchase storage space also on the cloud, and we could have a machine running entirely on the cloud space without my machine having to do anything with it. So that was when the definition of big data changed completely. So let me share my screen and come to what basically constitutes big data definition today. I hope my screen is visible.
Yes, sir.
Sure. So this is what we are looking at. Uh, I created a lab using Perplexity for all of you. So big data is in zettabytes. In 2025, it is considered that we would have 181 zettabytes of data on the entire internet. And it's not just about internet data, it's about also devices that we are using. There are 6 billion internet users, which is roughly 67.9% of the global population who use internet. A simple statistic is there are 231 million emails sent per second, or per minute, sorry. And there are 5 billion social media users, including Snapchat, Twitter, Facebook, LinkedIn, all the social media. And the biggest part of it is that 85% of all this data was created with the advent of social media, with the kind of data that we are generating, because we moved from text data to now images, audio, video. That is the primary way of how we are creating and consuming data now. And the second big statistic is that 80% of the data that we have in enterprise is unstructured. So your video data is unstructured, your audio data is unstructured, any text data is unstructured. Only that data which you put in tabular format or in JSON file, that is structured or semi-structured, that we have discussed previously also. And the third big thing is that 70% of the companies require real-time analytics on the data that we want. So we want to be able to load this data into some system, and we want to be able to process this data also to get insights from this data. I hope you are with me so far that I haven't put anything typically hard in the discussion yet. So let us see how the big data evolves. The evolution starts with the early era, 1663 to 1960s. In 1663, there was first attempt in statistical analysis where the first public collection of health records during the plague in England was analyzed. There were no computers, it was all manual. It was painstakingly tabulated using books, copies, paper, pen. And in 1884, the punch card machine, when it was brought in, because if you remember, if anybody of you is in from my generation, for that matter, so punch cards were input devices which computers were given, the big systems were given all inputs in the form of punch cards in the beginning. So punch cards were the first input devices or the inputs which were in bulk. So that was again constituted big data back then. From 1960s to 1990s, IBM introduced the large data processing by their mainframes. And in 1965, the first government data center was built by the US, and it was basically used for income tax. So, with 742 million tax returns and 175 million fingerprints of people who were submitting, that was the second very known collection of big data. And then we saw the internet. So, this I hope everybody has witnessed that from 1989 to 1990, World Wide Web was created. And with this came in a lot of websites on different domains, then turned into portals, then from portals to microsites, and we have a plethora of them. And trust me when I say this, that we see only 10 to 15% of the data on the internet, because a lot of it is hidden in dark web, and there is a lot of it hidden in the hidden web, both. I get a query. Yes, Herman Hollerith. Ah, that might have been a mistake there. Ah, Herman Hollerith was a punch card machine, correct? So then we come to that from the World Wide Web, we came into the Google domain registration. Google.com was registered. Search was revolutionized. We could now search across the different websites that we had all across the internet. There were search engines, crawl, spiders, which would check out each site for the information contained in it. And the search engine, Google was not the first one. There were search engines before Google also. Can somebody name any search engine before Google.com was launched? Let me see if anybody is from that time. Was Yahoo prior as a search? Okay, that's the homework for you. All of you would find that which search engines came in before. From that, we moved on to the big data era from 2000 to 2020. In 2001, the first definition of three V's of big data was given by Doug Lani. He coined volume, variety, and velocity, three characteristics only. Originally, these were the three V's of big data, but now the definition, sometimes people say three V's, five V's, seven V's, 10 V's, 14 V's also. So that is the kind of evolution, because with the characteristics of data changing, with the types of data, with the types of applications we are using, everything is now changing. In 2005, Apache Hadoop was created. So Hadoop framework, although it was created in 2005, it was not very popular till 2015, where we actually saw some enterprise applications coming in for this. Apache Spark was released in 2014, and I was fortunate I used both of them as a software where we could give it a large amount of data to be processed. It would break it into parts. I'll come to that, how Hadoop works. Okay. Internet Explorer was the first browser that you would have worked with because Windows had an advantage there. Thank you, Sheila. In the modern era, in 2020, now compare. In 2020, the total amount of data across the entire internet was considered to be 64.2 zettabytes. Okay. This was doubled within 5 years from it. That means from 2015 or 2014 up to 2020, the data volume, rather it was 2018, if I am correct. So from 2018 to 2020, from 37 or so zettabytes, we moved on to 64 zettabytes. That was doubled in 2 years. And it is expected that in 2025, we would be consuming close to 181 zettabytes of data. That is, so the up to 2018, the complete internet had some amount of data. By 2020, that almost doubled. And from 2020 to 2025, that is now reaching 3 times more than what we had in 2020. So this is the volume of growth of data that we are looking at these days. All right. Within this, we have seen that there would be structured data, which is roughly 20% of the organized data stored in databases. This is in rows and columns. Usually you can query it using SQL. The data types are fixed and the data integrity is high. So this is again a part of the hidden data as I spoke. So there is a visible web. Visible web is the all website that we see directly. There is a dark web that we do not see, normally not on our browsers. There is a different way of getting accessing the dark web. And then there is the hidden web. A hidden web is something which is almost like you can take an example of IRCTC website. You can log in into that, but unless and until you search for Delhi to Mumbai trains, you will not see that list coming down, that which are the trains available, what is the seat available. So that data actually, which is stored in tables and structured data, is somewhere in the backend in a database, but we can fetch it and see it on the browser by using our front end. So that basically is the hidden web. The data is there, accessible to the web, but not directly visible. It's not actually shown unless and until you run some query against it. So that part is the hidden data. And most of the structured data is usually hidden. Then we have semi-structured data, which is having some organizational properties. It's a little more flexible than structured. But this is more like that when websites started using JavaScript object notation or JSON and NoSQL databases, this came more into picture. Can somebody quickly answer what do you understand by NoSQL? If anybody has an idea, I'll have on the chat. Just anything goes with why MongoDB or why Cassandra or why these databases originate instead of SQL. Take a guess. What is NoSQL? SQL was structured query language. Monisha, perfectly fine. Okay. Akib says they are used to handle unstructured data. Partially correct. Unstructured data can be handled by my previous databases also. So in SQL based databases like Oracle, we used to have blobs. That blobs we would use to put in anything which would not categorize as structured. My question was that what is NoSQL? How is it different from the SQL databases? So, okay. Manmeet says these use handle data or manage data. Okay, I'll give you one example. So all of you understand SQL databases. That is my understanding that because this was something that we all learnt while we were studying. SQL databases had a fixed schema. Okay. Aishwarya is very close to the answer. NoSQL used to store unstructured data in JSON. very close. But JSON is semi-structured, so very close, not exactly true. So before NoSQL databases came, we would store everything in the form of tables. All right. Consider if you are using Facebook, right? If you are using Facebook and you have to store, what can all you store? So for any post, a Facebook post may have only text, single line of text. It may have text plus emoji. Secondly, it may have text plus emoji plus an image that may be there. It may have text plus emoji plus a video that may also be there. It may have all of these plus zero comments. There can be comment, there can be reply, there can be multiple comments. Now the problem is that all of these are variable. The first thing that there can be a post with only a single line of text versus there can be a post with text, emoji, video, hashtag, and in addition there are a lot of comments also. What structure supports this? Because if I create a tabular structure, I would have to devote a lot of space per record. And for each record, we would have a lot of empty values because we don't know whether somebody is going to comment or not. To bypass that, NoSQL originated. Now, MongoDB, as Subhashini has said, MongoDB allows you to create a document database. With a document database, what you store is a key value, something like for this field, there is a value. If there is another field present, there is another value. We store all of them together in a JSON format, store it in the database. But for anything which we do not have yet, that is not stored. So for NoSQL, there are different types. There are document databases, there are key value pair databases, there are graph databases, there are vector databases, there are multiple types of databases. But we are now working on a scenario where we would be able to store structured, semi-structured, both kind of data and unstructured also, but allocate only that much space which my data is currently in. If there is more space required, it would be added later. So that was about it. And then came in unstructured data. This is raw data without predefined organization. So it is highly flexible, rich in information, but always requires specialized tools to work with it. So text documents, images and videos, social media posts, all of that is unstructured data. So you can see the difference that we have in between these data types, between structured to semi-structured. Let us move on to the sources where the data coming from. So from the big source, the big data, the source distribution comes across. It can be coming from social media, which constitute 25% of this. IoT devices, which are sensor-based, constitute 20% of the data. Business transactions, web activities, mobile apps, system logs, research data, government records, and government records is the least of it. So what is the most valuable data is the least of the entire scheme of things. 15% business transactions, this is valuable, very valuable. And then 8% system logs, and this 7% of government record plus research data is considered to be the most valuable in this scenario. So social media, you see that Facebook, Twitter, Instagram, and we would come to with the three V's that we had. The volume of this data is very high. The velocity is real time. That means you can keep posting anything here or on Twitter or on Instagram and immediately goes on the platform. And the variety is also high because now we have. Do I hear somebody with a question? No. So this is something that we can variate between that IoT devices and sensors have the volume to be very high, velocity is real time, but the variety is medium. That means we would be looking at similar data coming from most of the sensors. The business transactions, again, the volume is very high, the velocity is real time, but the variety is medium. Okay. So this is something where is the data coming from. All streaming videos is another source of big data. So what happens in an internet minute in 2025? Let us see if we start a live simulation right now, then how much TikTok, Spotify emails that get generated per second, how it grows. Just see that while we are talking, there would be SMS, then Google queries, then YouTube, Facebook, Netflix. How fast do they work? This is the volume that we are dealing with. So on TikTok, between the now and the last 30 seconds, 312.5 million videos have been watched all over the world. That is the kind of scenario we are working with. All right. There are three big key data technologies that people work with. One is Apache Hadoop since 2005. It's a distributed storage and processing framework where the gist of the summary is you have got large amount of data, break it into parts, give it to different processors, let them work on it, combine back the results, and then give a consolidated result back to the user. But this was not, this was taking the data from storage. Apache Spark came, it changed the things. It actually had a in-memory computing. That means whatever computation that we were requiring to do, that was actually being done in the RAM itself. The processing became faster, real time, and there was multiple language support with Apache Spark, with Hadoop was missing out on. Apache Spark came from the same family. It was coming from the same background of how to distribute data, but it was almost 100 times faster than Apache Hadoop, which came. And then we have NoSQL databases also, where you would have a document database like MongoDB, key value Redis, column databases like Cassandra, or graph databases like Neo4j. And recently we started storing, because of LLMs, we want to store vectors in the databases. They are called vector database. All right. So this is part one of the presentation. What happens in the future of big data goes into that we would require to have edge computing, process the data closer to where it is generated. How do you add high compute to your systems? So in our case, we are working with a robotics project, for instance, and for that, because the robot is looking at a lot of things, it is capturing a lot of information. We want to make it that data process right away, not at the cloud, because it has to be real time again. Otherwise, it is going to pick up something and it is going to keep on buffering the data coming from the cloud. That can't be possible. So we are using some NVIDIA devices attached to the robot, which are high computation. So that constitutes your edge computing. We are looking at quantum computing estimated to be coming in full flow by 2030. This is exponentially faster processing. We have already been witnessing AI and ML integration from 2024 onward. So there are automated insights, predictive analysis, intelligent data processing, and self-optimizing system. And it is currently 75% integrated with our system. And then we are also looking at real-time everything. So we want whatever data that we are uploading, there should always be insight available instantly. So real-time everything is very closely associated with AI/ML integration. That is what is happening. And looking at 2020 data patterns and 2025, we are prophesizing that we are going to have almost three times data in 2025, which was doubled in the last 2 years previous to that. So we are swimming in an ocean where data is in bulk. If there are any queries so far, please ask. I'll be happy to take them. Post them in the chat and we can see.
Good evening, sir.
Yes,
So this side, Gurminder. Sir,
please.
my question is this thing, like you were saying, the edge computing and quantum computing. There it is written 40% adoption. how we can explain this thing adoption over here?
Okay. To the students,
Yes, sir.
edge computing is 40% adoption means that, see, there are three things here. One is that the compute devices, uh, let us say, you can take the example of OpenAI or you can take the example of Grok or any LLM model.
Yes, sir.
What they are doing is they are storing in a huge amount of data, but they don't store the data on the cloud or they don't take the compute away. They are setting up supercomputing clusters which are actually deploying lot of NVIDIA chips within that same cluster. So this became 40% only because that NVIDIA chips, I mean, it's very hard to get your hands on one single GPU from NVIDIA.
Yes, sir.
My, if I have to set up a GPU in my college, for instance, it
Mhm.
would cost me close to 4 crore rupees for that uh, A100 or H100 system that we have. They're very expensive because of setting up the infrastructure.
Yes, sir.
Now consider uh, 20,000 or even 100,000 of them lying with Elon Musk, who is actually leading Grok as a part of the Twitter. And Grok is absolute real time because there are a lot of tweets happening every time, every minute.
Yes, sir.
And if you open Grok and ask it a question that what happened in the Alaska summit between Putin and Trump, it would be able to analyze all of the tweets available on Twitter, fetch out which are the most important ones. It would also search the web, collect that information, and in real time, it would give you an analysis of what is happening in this domain right now.
Yes, sir.
So that is the big part of the edge computing where we are setting up huge clusters. But in small setups, if I have to create a small robot which would be able to uh, look at the world from its side, or a Tesla car, for instance, where the Tesla car is self-driving, it
Yes,
has
sir.
to keep on looking at the environment, keep on in real time process. If there is a tree ahead, then take a turn, or if there is a car ahead or something happening, that is happening within the device. The data is being generated right away. It is being computed. The reaction has a real time analysis required. And that is again a case of edge computing being taken.
Right. Thank you so much, sir. Thanks a lot.
Please. Any more questions? Quantum we are not looking at right now. I mean, quantum is in research phase, majority restricted to lab, but there is a very good progress happening in this. Okay, so let's go from this to, would you like to see how Hadoop works?
Yes,
I'll
sir.
take
It
it.
will be. It will be very nice, sir.
Right.
Thank you, sir.
So there goes in Hadoop, looks something like this. I mean, I could not simulate it exactly how Hadoop looks, but Hadoop has a distributed file system, one part of it, HDFS that we call. MapReduce and Yarn were the two other components of Hadoop. MapReduce was the processing framework for parallel computation across distributed data. Yarn was a resource manager. So it was yet another resource navigator. If I remember the name correctly, that was the name Yarn came from. It manages the cluster resources and job scheduling across applications. So first thing first, that if I had to set up a Hadoop something, I would find say 100 of my computers or PC boxes that were lying around. They might not be very useful now, but all of them have some storage, all of them have some compute. Okay. I would connect that to one Hadoop machine, which is having a name node. That name node, what it does, that it would manage the metadata. It would understand where is my file system located in all the machines which are connected to it. And the 100 machines which I found lying around or which I wanted to connect to my Hadoop system, all of them are, they may be local to my locality. They may be spread in the city, they may be spread across the world. But what it can do is the name node is going to understand where each of these devices, how is my file system scattered across these, and it would be able to now understand that if I store something somewhere, how to address that, where is that located. So what Hadoop would do, it would break my data. Let us suppose my file was 1024 MB of data, and my nodes can take up only 128 MB of data at a time. So it would break that data into parts. It would not keep that data into 1024 MB together, because that was not feasible for any of the machine. But it would break it into chunks of 128 MB each. That is default. It could be lesser. We could configure it to be 16 MB. It could be more. We could configure it to be bigger, depending on what is the storage capacity of each of my devices. And then it would also keep copies, that if I have stored some data on machine 1, I would keep two more copies of that in some different machine, because if somehow my machine 1 is lost, or it breaks, or it is not available anymore, then I have the replicated data available elsewhere to maintain reliability of my system. The second part was map reduce. It would transform all input into key value pairs, that for this query, what is the value? It would shuffle and sort, group and transfer intermediate data, and reduce. That means it would aggregate the group data back into a final input. So it was almost like, with HDFS, I broke the data into parts, gave it to different data nodes. On the data nodes, if I have to process, I will bring the data from the data node, process it, store it. But my MapReduce is going to eventually club all of that data together to give me a final result. So the resources were being managed by Yarn. So it had a node manager and an application master, that what application am I currently running on it? Because HDFS would be working with a lot of different applications. So my first application may be video processing, which has a lot of data. It might be running, the other application may be document processing, which may have a different set of data. So which application is using my system was the third part. Then it is something like a simulation where you would be able to see. So if I have a file size, my total file size was say 512 MB. Okay, and the block size is 128 MB. I could reduce it. The replication factor was 2 or 3. 3 was default, and I have 4 data nodes, suppose. Then what name node would do, it would process the file split, say one block here, one here, another here, creates 4 blocks with 12 replicas, and my storage efficiency is only 33%, because I'm not only storing the data, but I am repeating the data multiple times over. All right, I'm going to reset it, step through again. First thing is name node receives the data, processes the file split, then it puts the data into different blocks, and then we have that these are the data nodes which are going to get the data collected. All right, and that's how I'm going to distribute the summary, the complete block of data, which was big, now to multiple machines instead of a single one. This is clear. So I am having a big file size, breaking it into parts, putting it to different data nodes, and creating copies also to maintain reliability. Then came MapReduce. So we are taking a small example of, if I have to process this text, this could have been a complete book, a complete Bible, a complete Gita, anything. So we have some mappers which are going to map the data to key values, and then a reducer is a single reducer which is going to combine the result. So mapper 1 takes some data, processes it. Mapper 2 takes some more data, processes it. There are multiple mappers. They will each process data independently, but eventually they will all give the data to a reducer which is going to combine it back. Okay. So I'll just reduce the processing speed a little. and start processing. So first split was in two sentences. Then in the map phase, it actually mapped hello to a key. So it created each of the tokens one by one. They shuffle and sort from both of the mappers. And in the reduce, you are just counting that there were two hellos, two worlds, two times Hadoop was there, one time goodbye was there, one time bye was there. So instead of one single machine taking all the data, counting each word one by one, we split the data into two parts. We gave part one to first mapper, part two to second mapper. Then we shuffled and sorted because the data that we received back. And finally, we combined the results from the mapper one and mapper two. The task here is simply counting the number of occurrences of each word. That's all, which is doing. So it's a very, very simplified analysis of how the Hadoop system would work. Okay. This could be anything. I mean, this is a word counter program. I can give it the complete Bible. The number of words become too much. I can have more than two mappers. I can have more than two reducers also. But eventually there would be one reducer which is going to combine them all back. Then there comes Yarn Manager, which actually manages the cluster resources and monitors the job. So with my system, it says that node 1 is having 54% usage on CPU, 89% of memory is utilized, right? It is active. Second node is also active. I'm using 42% of its CPU and 77% of the memory. Third node is also active. So with CPU 31% and 84% memory. And node 4. Suppose if one of the nodes goes down, if let us suppose node 4 is not there anymore, in that case, because it is replicated in node 1, 2, and 3, we would still be able to process, but the distribution now becomes two less machines. So for uh, the load of CPU in these might become more. The memory in these might become more. All right. And this is your complete flow. So you start with ingestion of data. You submit the data uploaded to HDFS. Then MapReduce job submitted to Yarn. Yarn allocates resources to the application master. Data is processed across all the nodes, which are cluster nodes, and the results are written back to the Hadoop file system. So this is a traditional comparison that if I had a traditional processing time was 120 minutes, then Hadoop with two nodes is going to reduce it to 80 minutes. With four nodes, it was only 40 minutes. And with eight nodes, it goes to only 20 minutes. I see another query coming up. Absolutely. So Ritu ma'am, all the nodes are working on similar process in Hadoop at a time because every single node which is computing is having the same algorithm for computation because we are simply not just distributing the data, but we are also asking each data node to process that on that same processing that is happening and return the results of the process back to us. I hope that helps the answer. Any other question for Hadoop so far? I'm enjoying this. Okay, so this was Hadoop. One good thing happened that why did we have to abandon the program for Hadoop from our BTech program? Because you don't see anything like Hadoop anymore. You don't even notice that there is something which is doing the distributed processing now. There is a reason. It got assimilated in the system. So big data computing is now considered to be an essential part of any application. So majority of the enterprise systems, they make it a part of their culture. They make it a part of their infrastructure. So this is something which is essential to them, but which is not visible. We wouldn't require somebody to manage Hadoop anymore. It has become a part of the system. It has been done and dusted, tested properly. So whenever there is a big data coming, the data center is going to invoke some way of distributed computing, distribute it, collect it back, even without us knowing. So that is why Hadoop went out of the curricula for the BTech program, because this became a part of the assimilation process. So it's a technology which is running in a lot of different companies, but silently as a bottom worker, which is not visible. Okay, let's go on to my third part.
Excuse me, sir.
We have a, yes,
Sorry to interrupt, sir. So we can say this thing that Hadoop is working at the back end.
you can say Hadoop is working within the system. It has become a part of the system where we are having a lot of processing happening. So when big data systems are working, they use Hadoop, but Apache Spark. Now, Spark is 100 times faster. It is a lot of improvement on the basic HDFS system which was originally launched. So yes, a lot of systems use Apache Spark within themselves when they are processing data.
So we can say, sir, this is evolution of how the things are getting over there in big data.
Yes, it is something like with evolution, it did not fade away. From Hadoop, we went to Apache Spark. Apache Spark is still being used, but in a non-visible, it's something like it became an abstraction.
Okay.
So when we are going to a higher level of work, the previous one is still there, but it is not now consciously being used. It became a part of the process which is subconsciously being handled.
Okay, sir. Thank you, sir.
So let's go ahead with the last demo of the day. So we have taken in 10 V's of big data with one single example. So we are taking a smart city IoT use case where uh, it's a hypothetical smart city initiative where we have a modern smart city with 50,000 IoT sensors. We generate 2.5 billion readings every day, and we would see all the 10 V's of big data in action here. So there are 2.3 million citizens, 50,000 IoT sensor nodes, 843 7 terabytes of daily data being generated, and we will see how does it say. So the first thing is, first V is the volume. Volume defines the scale of data. How much data is being generated by the IoT sensors, camera, citizen interactions in our smart city? Okay, I have another question. Jyoti ma'am, thank you so much for the honor. I'll answer it separately. So volume is about the scale of data. You have the massive amount of data being generated by IoT sensors, cameras, and citizen interactions. So people might say, click a photograph, there is this place has not been cleaned, that goes to your volume. So with a city population of 2.3 million and 50,000 IoT sensors, this is how my data is going to keep on increasing, right? So currently my data may be out of the 1.2 petabytes. I'm just storing 847 terabytes of storage today. The data is coming from traffic sensors, where there are 12,000 sensors, environmental sensors, energy grid, citizen apps, which all contribute to the data. If my population goes up, then accordingly I need more sensors for, and the storage would also increase. Uh, yes, good question. IoT data can be hacked, certainly. It's a very different journey, although. So the second part is velocity, with how fast is our data coming. So from traffic flow, I might be having data which is coming very fast. So there may be so many entries coming per second, 2427 entries per second. Emergency data is lesser, and environmental data is again going to be high. So emergency response should have an automatic dispatch within 15 seconds of incident detection. And that is basically making for the speed of data. So we want that the data which is essential gets a higher bandwidth, and the data which is less essential gets a lower bandwidth. we can work with the 90 millisecond system latency, which is optimal in this case. And the data should be processed at this 99.7% of the data is being real time processed. Okay. So uh, traffic light timing is optimized based on the volume of the real time data. This is about the velocity of data. The third thing goes into variety, where my data is structured, sensor reading, temperature and pressure, GPS coordinates, database records and transactions. It is again semi-structured, which is JSON, API responses, XML configuration files or log files. And some is unstructured data, which is social media posts, video feeds, images, audio recordings, and so forth. So we normally integrate the data by using a ETL process. So we will be collecting sensor data or the other database, extract, transform, and load. It goes to a data lake, and finally we apply the analytics on it. Right. So it's a small simulation which actually says that the entire process of the data being taken, processed, and with a good quality, the processing time goes to 3.2 seconds. That is something that we call as a real time. So variety is the types of data. Veracity is the quality of data, that how good is the quality of data that we are getting. So overall data quality in our system can be this, that 96% is accurate, 93% complete, and 94% consistent data is there. So some issues may be there, like 5.8% false positive in traffic sensors can be there, or 2.1% sensors hardware are failing. That may again be there. Or there may be 9% noise in citizen reports. Some people are making false reports, or by mistake or something like that happen. So our data may be validating something like I may have a temperature value coming to be 456, and it says that temperature reading is normally it's outside my operation range. Or if my traffic count goes up to 60,000, and they say this is not good. Maximum expected is 10,000 vehicles per hour. So this is a low quality data. It's invalid. So if I have only say 5,000 traffic, so this is 95% quality score, the valid count there. So that is about the data quality. So my system is supposed to actually check for the veracity also. Then we go into what is the return on investment, that how much value is this collection of data and processing giving me back. So my traffic efficiency is 30% congestion reduction. That is an ROI. I have 25% energy savings, so cost reduction. That is a return on investment. Emergency response time is 18% faster, and citizens are 40% more satisfied. So that is the value that we are deriving from it. So there is an annual savings of 12 million US dollars. That is again additional. So if you had an investment of $15 million and there is an annual savings of 12 million, so you can pay back for this within 1.3 years. That is the kind of value that we are deriving from this data. Then comes the validity of the data. How far, how long is my data valid? So for traffic data, it has to be immediate. For air quality health alerts, it can be a little later. So it can wait a bit. For emergency, it would be exactly immediate. So we have to check for appropriate data usage, what is we are using it for. If somebody is using location data to send unauthorized advertising, that is inappropriate data use. So this is something that we have to control also. So we have to see the compliance, that who gets access to which data and for what purpose are they using. And for this, there are several laws, including the GDPR, and consent management has also to be there for data governance. So the next question was asked earlier, how vulnerable is my data? Can the data be hacked? So if we have 100% data encryption from end to end, we believe that the data is secure. That is something that we have to invest on. Our intrusion detection systems, and they detect 99.3% correct. So we see that there are no major breaches in 2024 in this simulated system, but there are possible infrastructure attacks. IoT vulnerabilities can be hacked by people. Somebody may hack the sensor system and show more traffic in some location. So that is something that is possible if my system fails to understand the intrusion. So unauthorized access to citizen personal information is a medium risk, while infrastructure attacks remain the high risk. So you can simulate a cyber attack with unusual traffic detected from so and so IP, yeah, multiple failed login attempts, or suspicious IPs automatically blocked, or something is escalated to the security team. But that happens with the incident response teams within smart cities. Okay. Then comes the volatility, that what is the lifespan of data? How long should we preserve it? So normally we keep in three types of storage: a hot storage, a warm storage, and a cool storage. And there is the archive where we dump the data when we do not need it anymore. So all real-time traffic data and emergency alerts are kept for 1 hour. It is the most expensive type of storage. Then air quality readings and sensor maintenance logs are kept for 30 days, which is kept in warm storage, which is a little cheaper. And then there is cool storage where energy usage pattern or citizen service requests are kept. This data is stored for 1 year, which is lesser cost. And demographics and urban planning data or census data that can be stored into archive, which is very cheap as compared. So you can check for that how much is the amount we would require to invest in the system. The next V is visualization, which is representing data. Most of these smart cities would create a dashboard where in real time they can see that how is energy being consumed, or how is the traffic flowing in our system, or we may want to see a line chart of the traffic data that shows across the different zones of the, or we may want to see the line chart of the energy usage across 4 zones, or the air quality. So this would be changing with respect to each of these, the dashboard. So that visualization is the next V, which is data representation. Finally, variability, that how is my data changing? How is it fluctuating? How far am I getting the same amount of data every day, or is it widely fluctuating? Are my sensors giving me similar? So rush hour traffic spike, like 6 a.m. the traffic is less, 8 a.m. it is higher, 12 p.m. it goes down, 5 p.m. it goes up again, 10 p.m. it goes down. The daily pattern is varying. So this is the variability. But weekends, we see in the business activity there is a very less activity, but on weekdays it is more. So you may actually again simulate that depending on the load, we may see if there is some traffic showing higher than this normal daily pattern. So variability, it simply talks about that how changing or how variable my data which I am storing is. I hope that was the 10V that we had to cover for this, and I am opening this for queries now if there are any.
Excuse me, sir.
Yes.
Sir, can you explain the seventh point, vulnerability, once again?
Which one?
Vulnerability, sir.
Vulnerability talks about how far my data is, uh, that how many attacks or how much is it vulnerable to attacks by people or to misuse. So this is about data security. How far is my data secure? Am I making enough efforts to keep it? Are there firewalls? Are there intrusion detection systems? Uh, is there enough safety in place, or is my data not secure?
Thank you, sir.
Any other questions? I'm looking at the chat window. This is open. Hitesh, it's not a website. I'll try to. This is something that I create for my lectures, but will do. Try. Let me see if I can make it public for that matter. I hope to share this on the SCS hub if Ashish sir would permit, and we'll see. We can take it from there. All right, I guess that's my time. There is a feedback link. Thank you for the nice feedback that I'm going to receive soon. Manmohan sir, your take, please.
Yeah. Thank you. Thank you very much, Dr. Gupta, for an excellent session. Excellent, truly excellent. Even I enjoyed it. And I hope the teachers, those who tuned in, must have been benefited by it. And our AI webinar series continues, and you will be duly informed, all teachers. Do tune in. Thank you so much. Have a Krishna Janmashtami, wonderful Krishna Janmashtami. Congratulations, and wishing you all a wonderful time ahead. Thank you.
Thank you so much.